Hello, fellow problem solvers. So today we're going to be doing a lesson in double counting or counting in two different ways. I like to call it double counting. And here's the thing. I'm going to make this a series of double counting, and I'll post other problems which have counting in two different ways, the technique that use the technique. However, I will not put that in the name. I'll create a separate playlist for this technique, which if you want to practice the technique and solve problems which use that technique, sort of to get better at that, you can click on that playlist and just listen to the problems there, right? Here we're going to try to just do these two introductory sort of problems, set up a principle, and then I will let you to it to decide if you want to do this by playlist, where you know that double counting is the way the problem is solved, or if you want to solve problems and then, oh, look, I've applied counting in two different ways. So that's going to be up to you. I'm just going to give you this big introduction. And we're going to do these two simple problems which have the principle of counting in two different ways. The first problem says that in some class, a third of the physicists are also mathematicians, and half of the mathematicians are also physicists. Does the class have more mathematicians or physicists, right? So we don't have directly the amount of physicists or mathematicians the class has. So we try to see if we can count some quantity in two ways. Can we count the number of mathematicians or the number of physicists in two ways and get to our desired inequality, whether there's more mathematicians or physicists? So let there be F, how many? P physicists and M mathematicians. The first thing says that a third of the physicists are also mathematicians. So that means that a third of physicists are also mathematicians, and a half of the mathematicians are also physicists. So now I invite you here to pause for 5 to 10 minutes and figure out what does this mean, okay? And here's sort of the next step. So here, what we have is we don't really have any way to sort of say one is greater than the other just by doing this, just by counting how many mathematicians or physicists there are, right? Because a third of physicists are mathematicians. Well, that just means this is greater or equal to M. And half the mathematicians are physicists. Well, this just means this here is less than or equal to P, right? This does not give us whether P or M is bigger. So we need to figure out another quantity that we can count here, right? And what is that going to be? Well, it's the number of people that lie on the intersection of mathematician and physicist, i.e. the number of people that are both mathematicians and physicists. And how do we do that? Well, in this intersection, what do we know? We know people that are mathematicians and physicists. On the one hand, they are, so every mathematician and physicist, we know that. So the first claim says that a third of the physicists are also mathematicians. So if there are k people here, right, then we know that a third of these physicists are also mathematicians. So a third of k is in here, right? Of the physicists, a third are also mathematicians. So k is equal to a third of p, right? And now of the mathematicians, so of those here, half are also physicists. So k is equal to, on the other hand, half of the mathematicians. And now we have a relationship between the number of physicists and mathematicians. And that gives us that m over 2 is equal to p over 3. Or now, which one is bigger, p or m? M is equal to 2/3 p, which is less than p. So p is greater than m, i.e. there are more mathematicians, there are more physicists in this class than there are mathematicians. So this finishes up the first example, sort of a toy example to figure out what is counting in two different ways. you can't count fit. You try and find a relationship between mathematicians and physicists. You can't find it directly, so you try to have this other quantity, a mathematician and a physicist, which gives you the desired relationship between the number of mathematicians and the physicists. In fact, there are the number of mathematicians is 2/3 the number of physicists. So this finishes up this first part of the problem. And now the second part. Here I invite you, try this out for 5-10 minutes. And here is the big sort of idea that I want to show you with this problem. And that is namely that, so what do we have? We have 1, 2, 3, 4, 5, 6 subsets of the set 1 through 8. The size of every single one of them is 4. And every single element here is a member of exactly k of the 6 subsets. We need to determine what k is. So here, the reason I like this problem is because it has a technique. It's one of the used techniques in counting stuff in 2 different ways. Like here, we've been counting really pairs, right? A person that's also a mathematician and a physicist, actually, now that I think about it, calling them pairs is a bit of a stretch. But we've been calling these, we counted this quantity here. And here I want to show you the idea of a sort of an incidence, I think, is the way you pronounce it, matrix. Namely, every single one of the elements, right? So elements 1 through 8, elements 1, 2, 3, 4, 8, are going to be members of some of these 6 subsets, right? And what we can say is, if 1 is an element of A1, then we can put a little dot here, right? Put a dot here, a dot if it's an element of A3, and no dot if it's not an element of any single one of these. And now this gives us a way to think about the condition in 2 different ways. And I invite you to pause for 5 to 10 minutes and figure out if you can determine k from this. And here's the big idea. The idea is, so let's look at the 2 things. So the size of AI is equal to 6. So it says that in every column here in this matrix, we have 6 dots. That's what this first condition tells us. So how many dots will we have in total if we just count the columns? Well, if we count the columns, we will have, how many? We will have 1, 2, actually it says 4. We'll have 4 times 6 dots, which is going to be equal to 24. On the other hand, if we count the rows, how many do we have? Well, it says we have every one of these is in exactly k of the 6 subsets. So we have k in every row. The number of dots is k in every row. And we have how many rows? 1 through 8. We have 8 rows. And this also is equal to the total number of dots in this matrix. So now k times 8 is equal to 24. Is equal to this thing, which is 24. So k times 8 is 24. In other words, k is equal to 3. Now, this is a very much and this finishes up the problem, right? K is 3, we're done. This is a technique where you're looking at the problem overall. It's almost like you're, I don't want to say averaging. These examples are a bit more intuitive than another one. I'll actually make another problem that's going to be double counting part 2. But the reason this can sometimes be unintuitive. In these cases, I don't know if it's not or it is. I find it fairly intuitive here that this has to be done in counting this quantity somehow. But it can generally be difficult to people because it's a technique where you're looking at things globally, overall. You're looking at averages, or you're looking at the whole system. I mean, here it asks you something about the whole system. It tells determine k. But sometimes in problems, it's going to ask you to, say, find a subset that has at least 5 elements. And the way you do it is by counting literally all the rows and then average out over the columns. And then you will then have that there's a subset with at least like 5, 3, whatever number of elements, or at most. But that's the way you sort of do it. Like, That's why this sort of technique is called global, because you're looking at the problem as a whole. You're not looking at a specific subset or a specific set that you're trying to define and say, for this thing, the problem condition holds. You're looking at things generally, averaging out. Here it makes sense. This solves our problem. We're done. And as always, thanks for problem solving.